So this is going to be a talk about advanced black hat attack techniques against Android. We're going to ask the question, what is the most effective and most stealthy way to gain complete control of an Android device? And in order to answer that question, we're going to be taking a deep dive into Android's internals. And in that deep dive, we're going to discover a system component which is little researched and little known, but at the same time is so central to the architecture of the system that any attacker can actually compromise that component and gain control over it will immediately have full power over the system. So welcome to man in the binder. He who controls IPC controls the droid. And we'll present our research in the form of a story. It will be a hack in 3 acts, if you will. In the first act, we'll focus on the architecture of the system and specifically on those parts we need to know in order to understand the attacks. In the second part, that will be the fun part. We'll actually attack an Android device. We'll attack a target application. And we'll do it from the perspective of 2 attackers who come from different experience levels and different knowledge levels of the system. And in Act 3, we'll show you how you can prepare your clients and your devices against these kinds of attacks that we're going to present today. So like every good story, our story has a cast. Can everybody see this? Yeah, I think it's OK. Fine. So first, there's us. Myself, I'm Nitai, and this is Idan. We are co-authors of this research. We work for Checkpoint in Checkpoint's Special Vulnerability and Malware Research Group. Our group basically deals with advanced security research. And you may have seen our work in the recent DEF CON. We'll also be probably presenting at CCC. So watch this space. And then the main character will be a victim application. It's a serious Android banking application. And like most banking applications, it's meant to transfer funds, to receive funds, and to check your balance. And our attackers would like to attack this application simply because they want lots of money. This is the noob attacker. He doesn't really know the system that well. He is not really aware of how the internals work, but he is still willing to try. Now, this attacker basically represents most of us as we approach Android. Most of us don't really know the system that well, so we'll see how that works out. And then there's the ninja attacker. He's spent months studying the system before actually lifting a finger against it. And we'll see how his attacks differ from the noob and what he knows that the noob doesn't. We have Android system services. They're kind of silent actors, but they're really important. They keep the whole system running, and we'll understand why. And we'll have the Linux kernel, which is, like any other story about Linux, a central actor in this story. But as you see in Android, the kernel is not as important as in other Linux systems, and we'll understand why. And now we come to our main mystery, all-powerful character, the binder. You may have not heard about the binder, but it's actually handling your most transactive data behind the scenes thousands of times a minute. And we learn all about the binder today, but the one thing you need to understand now is that everything goes through the binder. And now let us start with Act 1, in which we'll learn about the architecture of the system. And for that, I give you Idan.
Hi, everyone. So first of all, in order everyone hear me? No. Do like that? OK. So first, in order to attack a system, we first need to understand the system. And to do that, let's first take a look at another operating system that we all know and some of us like, Windows. So a typical Windows application, when it wants to do something really simple, like play a sound, what it basically needs to do is know what kind of a kernel we have in our application. It needs to know what kind of a syscall they need to use. They need to enumerate all the audio devices in the system. They need to send this syscall. Basically, they need to know a lot of information in order to do something really simple. What this is basically means that our application is really heavy application. Now, I'm not saying that the programmer needs to know all this information. What I'm saying is the compiler knows all this information. It will embed all this information inside your application. And this is exactly what the Android designers wanted to avoid. So in Android, the first thing they did, they wanted to build an object-oriented operating system. And in order to do so, the first thing they did, they wanted to isolate the application from the kernel. So when an application will try to speak directly to the kernel, it will fail. They introduced a new concept called system services. What it basically means is these system services is responsible for a specific part of the kernel. For example, if we want to take a picture, we need to talk to the camera manager, and the camera manager is the only one that is responsible on doing all this complex information for the kernel for us. So this is all nice and fun, but we still have a question. If we say that we can't talk directly to the kernel, how can we speak with the other processor? So in Windows, the processors speak with one another through the kernel. In Android, we have what is called the binder. So the binder is a simple inter-process communication mechanism that is in charge of passing the remote procedure calls to the required services. For example, if we want to play a sound, our application, we need to send a remote procedure call to the audio manager, and the audio manager will handle all this transaction for him. Okay, so now let's take it and remember, everything goes through the binder. It's a very important thing here, so remember. Now let's take a look at how Android developers implemented binder. So they implemented it in two parts. The first part is a user-land framework part that is responsible on wrapping the remote procedure call into some special container, and another part called the driver kernel, which is responsible to pass that information to the required process. So again, our example, when we want to play a sound, we'll need to wrap that information using the user-land part. We'll send it to the driver part using the IOCTL syscall, and then unwrap it again using our user-land framework into the other application. And he will talk for us to the driver, the specific driver. Now the parcel is basically a flexible, extendable data object that is will have all the information that we need in order to invoke the remote procedure call. So the first thing is we're going to have the destination. As you can see right here, we have the destination for this time is a media player. So we're going to have a string to where we're supposed to go. After that, we're going to have the function code. The function code is going to tell us which function we want to invoke in the other side, and then we're going to pass the arguments to this function. In this example, we're going to send two numbers, the left volume and the right volume, and in this case, it's ones. Okay, now let's do a short recap, just to see that everyone understands what happened until this point. So when our application wants to play a sound, he will send it to the user space part, and then he will wrap it inside a parcel. The parcel will be sent into the driver part. The driver part will parse that information and pass it to the required process. And then again, he will send the right syscall in order to play that sound in the system. Okay, so this is like, now you can see the real picture of Android. Now you can see what's really going on. We have a lot of applications. Those applications are sending a lot of requests through the binder. We have a lot of system services that are receiving those requests through the binder and handling all the communication. What I'm basically trying to say here, everything goes through the binder. And now for the fun part, I'll give you Nitai for some really cool attacks. Nitai.
So you ready for some entertainment? Well, in this act, we look at some really popular attacks against Android, and we look at the old way of doing them, and we look at the new way that we think they'll be done in the future. Well, we'll have 3 rounds. And we'll have our 2 attackers having a face-off. Again, I remind you, we have a noob attacker and a ninja attacker, and we see the differences between them. And the first target is the most simple, the most common kind of attack you'd want to have against a device, keylogging. They simply want to capture the keystrokes of the user, specifically when he's putting in his user and password into the banking application. Let's see how the noob attacker actually approaches the problem and how he sees the system. Well, a noob attacker doesn't really know the system that well. And what he sees is that there is a keyboard server, which is a system service, for which our application basically registers, and it receives the keystroke data from that server. So there's this back and forth going through from the application to the server, and that's how the keyboard data that gets sent. And that's what the noob attacker sees. Now, in order to attack the application, the noob attacker uses a very simple approach. He's using social engineering. He basically tries to manipulate the user into installing a malicious keyboard application, which would then just grab the keyboard data and send it to a CNC server. Now, this is a very common approach It's surprisingly popular. We might say that it's actually the only approach in the wild to implement keyloggers on Android. We've seen some recent attacks against it, imitating popular keyboard applications and causing users to install them. And the problem with this, of course, is that it's very easy to spot. All the user has to do is simply go into the application menu, see that a malicious keyboard application is being installed, and remove it. And antivirus vendors focus specifically on those sort of issues. They know how to identify malicious packages. They use hashing techniques to identify applications they need to remove. So this is a bad approach which doesn't really work that properly. Now let's look at how a ninja attacker would try to do it, and how, first of all, how he would view the system. Well, when a ninja attacker looks at the system, the first thing that he takes into account is that everything goes through the binder. And what does that mean in this context? Well, it means that as the keyboard data gets sent from the keyboard server to the application, to the banking application, it all moves through binder in those parcels we've discussed. So the only thing we need to do is capture these parcels and parse them and get the keyboard data out of them. And for that, we'll have a demo. I'll show you exactly how that's done.
Okay, so the first demo, what we're basically is going to do, we're going to inject ourselves into our bank application. As you can see here, we'll check the number of the process that we want to inject ourselves into. In this point, it's going to be 974. And now what you're going to see here is whenever we do a keystroke, when the keyboard will show up, whenever we'll see a keystroke, we'll see these keystrokes because all those keystrokes are passing through the binder in clear text. So for this first example, we implemented a keylogger.
Yeah. Are you? Yeah. So that was demo number 1, a pretty simple hack. Now, round 1 ends in clear victory to the ninja attacker because he understands the binder. Let's move forward. Let's look at round 2. Well, this is a slightly more advanced attack, and it's one of the most interesting, most popular attack vectors against sensitive applications. But in this case, a user uses a banking application in order to transfer funds from his account to another account. And what an attacker would like to do, the kind of most obvious thing to do, is to grab that data on the way and perhaps change it, perhaps move it to the attacker's account, perhaps change the amount. And that's what our two attackers would like to do. So let's look at how the noob attacker sees it. And let's look at how an Android application looks from his perspective. Well, an Android application is really just a set of activities. Each screen is actually an activity. And most applications play with those activities in order to present some kind of interface to the user. So in the case of our banking application, we'll have 3 activities that actually deal with transacting the funds. In the first screen, the first activity, the user will just put in the account number to which you would like to transfer the funds and the amount transferable. In the second screen, the actual transaction with the bank will take place. It will just be a waiting screen while the application talks to the bank servers. And the third screen will actually show a confirmation message and explain that the funds have been transferred. Well, what would a noob attacker do against this? Well, a noob attacker has a problem. He doesn't really know how to attack a process on the inside. He can't really access the internals of the application, specifically if we assume that the application is obfuscated, as most security critical applications certainly are. Well, what would he do? Again, he would use social engineering. He would cause the user to somehow uninstall the banking application and install a malicious application which looks and acts just like it, but instead of transferring the funds to the user's account, will transfer them to a malicious attacker's account. Now, this is also a very bad approach, again, because antivirus vendors look specifically for these kinds of attacks. Again, this is the most popular attack vectors, one of the most popular attack vectors when you're trying to achieve this on Android. And this is very easy to discover. You basically compare hashes of known packages. You look for malicious package names that you're aware of. And whenever these databases get updated of package hashes of malicious applications, the user will get notified. And this is assuming that you've managed to actually fool the user into installing your application. So this is no good. let's see how a ninja attacker would actually do it. And first, let's understand how he views the system. And now we're in for a surprise, because when a ninja attacker looks at the system, the first thing he takes into account is that everything goes through the binder. And this is kind of surprising, because if we've divided our view of the system into islands, and our application is an isolated island, and remember that Android is an object-oriented system, you're supposed to have encapsulation, why is it that our data, our most sensitive data, actually gets sent outside? So let's look at the internals of the system. What really happens on Android is that to start a new screen, you need to talk to the activity manager, which is a separate service, a system service, running in a separate process. And in order to do that, you actually need to talk to the binder. You need to send your activity data. You need to send your request to the binder. Binder sends it to the activity manager. The activity manager actually initializes the new activity. And then the application ends up in a new screen, in a new GUI. Now, it's not only that the application calls the activity manager in order to start an activity, it also has to give it all the data which it would like the other activity, the second activity, to have access to. In the case of this banking application, in the case of our transaction, we actually need to give it our transaction data. Now, most developers are not aware that this data is actually going to another process. So even highly security-aware developers will just send this data in plain text. And then, to complete the transaction, again, we'll call the activity manager to start the third activity, and that will be a confirmation message to the user. So what would our ninja attacker do? Well, that should be obvious by now. He will simply capture the data as it goes through the binder in plain text. And that's just like a sample buffer that we've captured. You can just change the amount, change whatever you want, and the application will not know a thing. It will just be presented to the next activity as if it's the real data. And in this attack, what we've done is simply changed the account numbers in transit.
Okay, now for the second one, we're going to log in again into our system, still without injecting ourselves into the binder. Now let's do a simple transaction. We're going to do from 222 to 444, and we'll give it, I don't know, a lot of money. Wait just a minute.
Which account is Kitty?
Kitty's account is the 222, and he will transfer the money to her friend, Idan, in this case. And then we'll see the transaction. As you see, we got the page of the transaction. The transaction has been successful. And as you can see here in the service part, we'll see that the transaction from Kitty to Idan was a success. And the amount is what we entered. Now again, what we're going to do is we're going to inject ourselves into the binder, to the binder of the application.
This is a mock server that we've set up to imitate the bank service.
Yeah.
So this is like the transaction as it's accepted on the bank service.
Of the serious bank application. Yeah. Okay, again, we injected ourselves into the bank application. And now again, let's do the transfer. Again, the same amounts. And as we see in the application, we still got a success. But if you can see the where to, we see that we change it to 1337. And we change also the amount just for the fun from 100,000 to 900,000.
Should have been $1 million.
Yeah, maybe next time.
Yeah.
You're ambitious.
It's good to be humble though.
Yes.
Okay. So that was our second attack. And just a personal note about that. I've worked with some banks before, like reviewing source code and all that. And it's really overwhelming how many banking applications use this approach. They just take a whole bunch of really sensitive data, like confirmation numbers, tokens, user accounts, amounts, funds, and all of this just goes in plain text as you've just seen. So you may say that our application is kind of like a demo application, but that's not the case. That's actually real in many cases. So that's a point to take home. So we have a clear victory for our ninja attacker, so that's 2-0. And now we have our final attack. This is also a really popular attack on Android, intercepting SMS. And in this case, the problem that our two attackers are facing is that when the victim user actually transacts funds, he needs to get some kind of confirmation SMS from the bank and just like put the number somewhere. That's also something quite common in banking applications. So our attackers actually need to intercept that SMS and get the confirmation number in order to get the money. So how would our noob attacker actually approach the problem? Well, in Android, we have a telephony manager, which is a system service that actually talks to the hardware and gets the SMS messages from the baseband. And we have our regular SMS application, which is just a normal user application. This is what most of us use to send messages. And this gets input from the telephony manager and presents the SMSs to the user. So what would a noob attacker do? Well, the most common approach in Android today to get SMSs is just to ask politely. You just cause the user to somehow install a malicious application which has permissions to read and to write SMSs. You grab the SMSs on the way, and you can just abort the broadcast so the user doesn't really see the SMS as it comes through. And that's what normally is done today by malicious banking malware on Android. And again, why is this a bad approach? Well, it's just easily discoverable. And a very common heuristic today in antivirus software is simply to scan packages for their permissions, just to open the manifest and look for any out of the ordinary permissions, something that shouldn't be there. And read SMS and write SMS are just the specific permissions that always raise the red flag. So it's very easily discoverable, and the user gets a prompt and uninstalls the application. So another fail, unfortunately, for the noob. How would the ninja approach it? Well, the ninja knows that. Anybody?
It goes for the binder. Yeah.
It goes for the binder. Yeah, that was easy.
Did it.
Yeah. So it really goes to the binder. As the telephony manager receives an SMS, it tells the binder, and then the binder, in a kind of complicated transaction, which we'll go into in a minute, sends it to the SMS application. And what the ninja attacker would do would be just to attack the binder in order to see the data. Now, why is this a more intricate hack? Well, a problem in Android is that the system is really complicated. I'm sure most of you are aware. And specifically, since we are running this malware in native code, it's kind of difficult to interact with the Java structures, which basically do everything above us. So this will be a sample of how we've actually gone around that. Well, what happens is, at the detailed level, the telephony manager is actually running a database. That is, it has a database of SMSs which have been received in the system. And whenever the database is updated, the telephony manager updates our SMS application. And the SMS application then has to query the telephony manager. It does it, of course, with a binder. And it has this really complicated function called, it's a database query in Java. And it returns something known as a cursor object. That is a common object in Android, but it's kind of hard to work with. Why is it hard to work with? Well, it's a very messy abstraction of a database response. You have this weird Java constructor, which is really hard to work with, especially if you have to instantiate these Java objects from C. It was a real nightmare. Actually, we've had a few sleepless nights over it. But then we kind of dug into it. We kind of looked at the buffer. We looked at what everything represents. And we found something very simple and actually very happy, that this, under the cover, this complicated Java object, this cursor object, is just a file descriptor in Unix. And what do you do with the file descriptor? You just read it. Very simple. And then you just get this dump. I'm not sure you can see it because it's a bit bright, but on the right, you'll see the ASCII where it says that you've got the confirmation number and all that. So this is what we got after reading the buffer. Again, this is an example of how you would take these Java structures and with a summary so just slice them to pieces and take what you need in C. And that kind of works for most approaches. And again, the ninja attacker won. So that's 3-0. It's a clear victory. So, yeah. So let's look at what just happened. Let's look at how these attacks against the binder actually work, because we've not been into that. And what happens in binder is that you have one hook to rule them all. This is the critical point. This is the point where the system calls the ioctl, which actually goes into the kernel driver. And it is right here at this very point that you can gain complete control of the system if you just hook this one place. Because all the data buffers we've described, all this sensitive information, it goes right here into this one place. This is a central point of failure, super important. So, and this also offers you a lot of possibilities for stealth, because you have a very complicated function structure all going down towards this point, because it all has to go through binder. And you can literally hook hundreds of points on your way to this. So any software which wants to look for you has a lot of work to do. And it has to really understand the system before it can find you. Now, this is an obvious question which some of you may have been thinking about already. Don't you need root in order to inject code into another service, another process? And the question is, of course you do. But we're saying that this is not really an issue on Android anymore. And what do we mean? Well, we have all these Android operating systems right up to KitKat. And the simple fact about all these versions is that all of them have rooting exploits which are just out there. They're very accessible. They're very easy to find. The most recent one was towel root, which works up to the most recent version. And we're saying that rooting on Android is no longer a big issue. I mean, you can just use any remote drive-by exploits to just gain code execution on the device, then use a rooting exploit for privilege escalation, and you're in the game. And then the next game is what do you do with that power? And that's what we're looking at here. How do you implement a perfect rootkit which does just what you want in a portable and flexible way? And you should just consider the possibilities. Let's look at, again, at how the Android system looks like from the outside. We have all these services, all these system services, all these applications passing around sensitive, important data. We have VoIP applications, we have Facebook, social applications, banking applications, and all of them need to talk to the binder. And we have the system services, which are central points in which this data goes through. And all of them have binder in their process memory, just ripe for us to hook and to get all that juicy data. So really the only limit to what you can do with this technique is your own imagination, because it's all there. It's all in the binder. So now let's look at, how are we with timing?
We have time.
Yeah. So let's look at how we actually need to prepare our system, what we can actually do against this kind of attack in order to make it less dangerous. And I should emphasize that we believe that this is actually the future of malware in Android, so we should all be prepared. Well, there are plenty, as I said, there are plenty of rooting exploits, and what this really means is that the Android security model that we all know and love should no longer be taken for granted. We should no longer say that we should count on a device not being rooted, because that's no longer a reality. And the problem we're facing is that antivirus software doesn't have permissions to actually fight the kind of threat that we're showing here. Android antivirus software runs within the sandbox. It runs within the security model of Android. So the question needs to be asked, what can we do? Well, first of all, a developer on Android and any security experts on Android need to understand that they have to take control of their own process memory space. This process memory is theirs. There's stuff that can be done there, and we can catch it. We can look for it. Second, we need to, if there's any sensitive data going through binder, going through IPC, we might want to minimize it. And we first of all need to be aware of what is it, and then we need to control it and see, does it really need to go to the binder? And there are steps that can be done against that. Well, and what do I mean? We'll come to that in a second. But regarding memory scanning, what we should do, like these are just solutions we should be taking home in order to counter this threat. Now, first of all, a developer or a security developer should scan memory for weird stuff that's happening there. In this case, our hooks that we've put. Again, this is a difficult task because stealth is really built into this solution because there's so many places you can hook. But there's a lot to be done by just scanning your process memory, protecting it using anti-debugging techniques. This has been done for years on Windows. Any secure Windows software uses these techniques like anti-debugging, anti-reversing to protect itself. And this also needs to be a reality on Android. Second, you should probably implement your own keyboard within the process in order to protect it. And what we mean is that we saw that all this keystroke data is going through the keyboard server. It's very transparent, it's all in plain text, and it's very easy to capture. It would be much harder for an attacker to capture the device as it moves within your own application if you actually implement your own keyboard as part of the application. And you need to remember to encrypt the keystrokes because it will all still go through the activity manager. And third, if there's anything important that goes through a binder, as we saw in the example of those banking transactions, you probably need to encrypt it. which is not the case today. So in the overwhelming amount of number of applications. So you will need to take control of it and encrypt it. So actually, yeah, we have a lot of time left for questions. So
We know you're hungry, so
yeah, we kind of did it quickly. So any questions? Nice slide, huh? Yeah. Oh, yeah. Yes, actually it is. It's very possible. Your own process. Well, Binder is basically a transaction mechanism. And in every process in Android, Binder is actually already preloaded. It's part of the zygote, if you know what I mean. So that gets forked and replicated into every application in Android. So yeah, you have it in your memory space. And anything that comes to your process, it's visible there. Exactly, yeah. There's tons of stuff you can do with this technique.
But if you already have root, why do you need to go to the binder? Why can't you target the application's memory space directly and read everything there?
Well, most backing applications I've worked with use reverse engineering measures. Lots of them use binary code by now. I mean, you'll have to start reversing ARM in order to understand how the application works. At the least case, you'll have to overcome obfuscation measures in Java in Dalvik. So that's not a trivial task, and it's not portable. I mean, you've attacked one banking application this way, you still have a problem. You need to reverse all the banking applications you approach. So that's really much less portable than just finding that one spot where all data goes through.
okay, thank you very much.
Thank you very much.